Okay, welcome to Lecture 1B, the chemical level of organization. You've decided after Lecture 1A that you think you like physiology and you want to keep on going. That's great. So in this remaining mini lecture, we are going to take a look at inorganic chemistry. You're going to think again, wait a minute, I've heard all this stuff before. And that's because you probably have. One of the prerequisites of physiology is a chemistry course like Chem 50 or Chem 60. Some of you may have even taken advanced chemistry courses like Chem 101, or you may have even have taken organic chemistry. That's okay. We are just going to basically review inorganic chemistry in this lecture, and again, touch on some of those fundamentals. The units of matter that form all chemical substances are known as chemical elements. Now, a chemical element is a substance that cannot be broken down into smaller constituent components through ordinary chemical means. The chemical elements that we're referring to are made up of atoms. Now, defining an atom is actually kind of a difficult thing. I mean, go ahead, without looking at this definition, try and ask yourself and try and explain to somebody what an atom is. It is the smallest unit of an element that still retains the chemical and physical properties of that element. There are 92 naturally occurring elements on Earth, and about 20 to 25% of them are essential to life for various organisms on this planet. These are needed to live a healthy life and so that the organisms can reproduce. And these 20 to 25% of those naturally occurring elements are referred to as essential elements. Now, out of the 92 elements on Earth, believe it or not, 96% of them are carbon, hydrogen, oxygen, and nitrogen. They are the four main essential elements that all life on this planet requires to survive. Coincidentally, about 96% of the elements in the human body are carbon, hydrogen, oxygen, and nitrogen. About 3.8% of the elements we find in the human body are things like calcium and phosphorus, potassium, sulfur, sodium, chlorine, magnesium. So that makes about what, 98.8% of the elements in our body? The remaining 0.2% are called trace elements. These are required by an organism in very small, minute quantities. For example, chromium, trivalent chromium, is a trace element that is required in our body for regulating blood sugar via insulin signaling. It's involved in the metabolism of fat, carbohydrates, and proteins. The trace elements are listed down here in this table. You've got things like fluorine. Fluorine is really important for strengthening the hydroxyapatite calcium phosphate matrix of our bones and teeth. Iodine is critical for the formation of the metabolic hormones T3 and T4. Without iron, hemoglobin would not be able to bind oxygen and transport it in the body. Even things like molybdenum and selenium and vanadium and zinc, these are in very small quantities in our body, but they're really important because they can function as cofactors in metabolic processes. Some of the naturally occurring elements on the planet can be toxic to humans. Now, while I mentioned trivalent chromium, hexavalent chromium with a charge of +6 is a carcinogen. It causes lung cancer. And just because it's toxic for us doesn't mean that other organisms can't adapt to this. For example, there are some plants that have adapted to what is called serpentine. There's the serpentine molecular formula down in the bottom of this picture. This is a jade-like rock which would contain toxic elements like chromium and toxic amounts of things like nickel and cobalt. They've learned to adapt to this toxicity. Unfortunately for us humans, this is generally not true. All right, an atom, the smallest unit of an element that still retains the chemical and physical properties of that element. It's a really tiny thing. Now, if I asked you to define an atom, you would probably say, okay, it's got protons and neutrons in its nucleus, and it's got a bunch of electrons that orbit around, and you would be right. An atom is composed of many subatomic particles. I'm going to stop you right here and tell you not to worry. We're only going to learn the basics of protons, electrons, and neutrons. We're not going to learn those really wacky subatomic particles like gluons and neutrinos. That's physics. We're physiology. Okay, what's a proton? Well, it's a subatomic particle that has a charge, one positive charge, and it has the weight of one atomic mass unit. Atomic mass unit is an arbitrary unit that physicists, chemists, they have given to the weight of a proton. The actual weight of an atomic mass unit is given there, 1.673 times 10 to the minus 24 grams. Don't ask me how they measured that. I have no idea. I'm a biologist, not a physicist. The protons are located in the atomic nucleus, along with its partners known as neutrons. Neutrons are neutral. They have no charge, but they have the same weight as a proton, so their weight is also an atomic mass unit. So the protons and the neutrons combine together to form the atomic nucleus, and orbiting around this nucleus will be subatomic particles known as electrons. Electrons have a charge of -1, and they are said to have virtually no mass, but you can see here that a mass actually has been recorded. So that is the basics of an atom. You're thinking, well, wait a minute, I learned this way back in grade 8, or I learned it in grade 9. That's fine. We're taking this lecture, this little mini lecture, to review some of the fundamental concepts of chemistry. So don't just say to yourself, well, I know this already, because what if on an exam I ask you to define what a proton is? Or I ask you to go to the periodic table of elements and tell me about the subatomic particles of magnesium. This is low-hanging fruit. It's stuff that you should know very easily, but it's stuff you should know. So don't just take the things that you're going to learn in this lecture and sort of put them off to the side, because I'm going to test on this stuff. And these are really, really easy points for you to make. So don't dismiss this lecture. All right, let's keep going. So I've mentioned the periodic table of elements in the previous slide. And what is a periodic table of elements? Well, it is basically a table that contains elements. Sorry. The periodic table of elements takes the naturally occurring elements we find on Earth, and we group them according to their physical and chemical characteristics. Each element on the chart is associated with a letter, an atomic number, and an atomic mass. And you can find all kinds of periodic table of elements located online. They're really neat periodic tables now. You can click on each one of them. They're virtual. Click on one element and a page will pop up and you'll find out everything you wanted to know about that element. Back in my day, every single textbook you opened up had a periodic table of elements on the inside cover. Can't find that now in today's modern textbooks because all of this is online. But down at the bottom, for example, is, I believe, the link to where I found this periodic table of elements. Here are two elements that I just randomly picked out of the periodic table of elements. I've picked lithium and potassium. You can see each one of these has an atomic symbol, Li for lithium and K for potassium. These are often based on the Latin words. You can see also that we have an atomic number, which is going to be the number of protons. Now, when electrically neutral, in other words, when this atom has no charge, the number of protons and electrons equal one another. So in an electrically neutral atom, if you know the number of protons via the atomic number, you also know the number of neutrons. To figure out the number of, you know the number of electrons if you know the atomic number. To figure out the number of neutrons, all we have to do is just do a little bit of subtraction. I like to write the symbols this way. I like to write it with the atomic weight or the atomic mass at the top and the atomic number at the bottom. Because then to figure out the number of neutrons, I just do some subtraction. 7 minus 3, 4. That's the number of neutrons that are found in the atomic nucleus. 39 minus 19, that's 20. Potassium has 20 neutrons and 19 protons in its atomic nucleus. If you add those two numbers up, remember, the neutrons and the protons are the subatomic particles that have mass. If you add the mass of the neutrons and protons together, you get the total mass of that nucleus. So 20 plus 19 equals 39. That's the atomic weight of an atom of potassium. 4 plus 3 equals 7. That's the atomic weight of an atom of lithium. All atoms in an element have the same number of protons. but many can differ in the number of neutrons. Now, why do all atoms in an element have the same number of protons? Simple. The number of protons defines what the element is. Carbon has 6 protons. If you go to 7 protons, you don't have carbon anymore. If you have an atom that has the same number of protons but differs in the number of neutrons, you have what is called an isotope. Isotopes are atoms of an element that differ in their number of neutrons. Now, in nature, an element is actually a mixture of all of its isotopes. For example, carbon is a mixture of 3 naturally occurring isotopes: carbon-12, carbon-13, and carbon-14. Notice all 3 of these isotopes have 6 protons. That's because carbon is the atom that has 6 protons in its nucleus. Since these atoms are going to be electrically neutral, that means the number of electrons and protons equal. All of these isotopes have 6 electrons. But look what happens as we go from carbon-12, the carbon you find on the periodic table of elements, to carbon-13, to carbon-14. Notice the number of neutrons increases. When you get to carbon-14, you have now actually have a radioactive isotope, and I'm going to explain what that is in another slide. Just what exactly is radioactivity? And just what exactly is a radioactive isotope? This is physiology. It's not physics, so I'm not even remotely going to explain the concept of radioactivity to you beyond what you see in this slide. Remember that protons and neutrons are found in the atomic nucleus. I want you to imagine that this nucleus is being held together by a kind of nuclear glue. And anytime you add another neutron to that atomic nucleus, that glue has to take that neutron in and hold it in. There is only so much room that you can have in the atomic nucleus for extra neutrons. And if you start adding too many neutrons to that nucleus, the glue can't hold the extra neutrons, and the nucleus becomes unstable. The breakup of the nucleus releases particles with very specific energy, and that particle release is now called radioactivity. The breakup of the nucleus and the release of these particles can also be known as radioactive decay. There are 3 different kinds of particles that can be released over radioactive decay. Each of them have very distinctive energy levels. There are alpha particles, which is basically a helium atom, beta particles, and what are known as gamma ray photons. Now, more information about this can actually be found on your Canvas shell. So I'm going to take a little bit of time to tell you that for a lot of the topics you're going to learn in this course, there will be a corresponding Canvas reading page, a page that says reading, and you can actually go to that. And on those pages, I will emphasize a lot of the concepts we have in lecture, but I may add a little bit of extra information. And you're going to ask yourself, Professor, do I have to know that? Of course you do. Between the textbook that you are going to get online, my notes, and those Canvas pages, that's going to be what you are going to use as the ultimate textbook for this course. That information, all of that information, is what you're going to use to study for this course. So do you have to know about the radioactivity information I give on this slide? Yes. If the e-textbook talks about radioactivity, you got to know that. And then when you go to the Canvas shell and you find my little reading section on radioactivity, do you have to know that as well? Yes, you do. That's a lot of information. So you will notice things that are really important, I write in bold. You'll also see a lot of the times I'll write them in bold and red, just again, so it leaps off the page and you realize, oh, that's an important concept. I call this the bold print method. And this is how I studied in university. I started off by learning the things that were in bold, and I made sure I knew them. And once I knew them, I could build upon that. The things which are in bold are going to be the foundation of what you learn. So on this page, the first thing you'll see is radioactivity in bold. Okay, let's learn what radioactivity is. And once you have that as your foundation, you can start to learn extra things like the 3 kinds of particles that is radioactivity, etc., etc. Radioactive isotopes and radioactivity tends to scare people, and rightly so. Gamma ray photons can penetrate human tissue, they can enter into the cells, they can damage DNA, they can cause cancer. So it is okay to have a healthy respect for radioactivity. But believe it or not, we use radioactivity a lot in science. For example, carbon-14 is used in something called carbon dating. The radioactive decay rate of carbon-14 is phenomenal. It is, I believe, something like 12,000 years before a radioactive carbon isotope loses half of its energy. And everything on this planet which contains carbon is going to have a minute amount of carbon-14. So if you know just how much carbon-14 is found in that object, and you understand the idea of radioactive decay, you can use something called carbon dating to figure out just how old that carbon-containing object is. If you'd like a little bit more information on this and you want to read some really fascinating use of carbon dating, look up what is called the Shroud of Turin, T-U-R-I-N. This was the cloth that was thought to have wrapped Jesus when he was placed into his tomb. It is a religious artifact which is stored at the Vatican. And a number of years ago, the Vatican finally agreed to have a small section of the shroud cut up and sent to various laboratories for carbon dating. The idea was that they would come back with a date that was somewhere around 2,000 years. Instead, they came back, all of these labs came back with an average date of 676 years old. So the Shroud of Turin, which was thought to have wrapped Jesus, may not have wrapped Jesus, but some dude who died about 676 years ago. It's really a fascinating topic, so you may want to, when you've got some time, you can just Google that. Now, most of you, of course, are taking this course because you're going into medicine. And radioactive isotopes have a huge impact in medicine. They are used in radioactive imaging. For example, PET scanning, positron emission tomography. This is a medical device which is used in conjunction with a CT scanner. Those people which are undergoing PET scanning are given an IV infusion of a radioactive glucose tracer. This is called 2-fluorodeoxyglucose, and no, you don't have to know that, but that's the name of the tracer. But it contains the radioactive fluorine isotope. And the idea is that this radioactively labeled glucose would be taken up by cells undergoing mitosis. Mitosis is an energetically expensive process. You require ATP to undergo mitosis, which means cells are going to need sugar to make ATP. So the fundamental idea of a PET scanner is that very highly mitotic cells, such as cancerous cells, will take up a large amount of this radioactively labeled glucose. And you would see basically the radioactive decay of this showing up by the PET scanner. And then that region of radioactive uptake and decay would then be labeled on top of the CT scan, which would give the anatomy. So here we see the spot lighting up in the throat, and that would indicate the uptake of the radioactive glucose by a tumor located somewhere probably near the thyroid. It might actually be a thyroid tumor. And once you've identified the tumor, you can actually treat cancer using radioactive isotopes. Remember, these isotopes break apart and they give off energy in the form of radiation. And this radiation can be used to kill nearby cells. Two very commonly used radioactive isotopes for this is cobalt-60 and iodine-131. Energy is the capacity to cause change. Potential energy is the energy that matter has because of its location or structure. The electrons of an atom differ in their amounts of potential energy because their location around the nucleus of an atom differs. Each electron has a very specific location around the nucleus of an atom. and that location is associated with a specific amount of potential energy. So each atom with their various electrons at very specific locations has a certain amount of potential energy. An electron's state of potential energy is called its energy level or its electron shell. In chemistry, you probably learned what was called the electron configuration of an atom. What that is a description of how electrons are organized around the nucleus. For simple elements, for example, the first 3 rows of the periodic table, electron configurations are described using the Bohr model. Beyond that, you got to get really fancy, and you get into the realm of quantum physics, where you now have to talk about magnetic spin and momentum and things like that. And again, this is physiology, not physics. Lucky for us, the majority of the elements that are found in the human body and figure very, very prominently in physiology are found in the first 3 rows of the periodic table of elements. Remember, 96% of all the elements you find in the body are carbon, hydrogen, nitrogen, and oxygen. And those are found in the first, 2 rows of the periodic table of elements? Add in things like sodium, potassium, lithium, you're still in the first 3 or 4 rows of the periodic table. So lucky for us as physiologists, the Bohr model will be just fine when using to describe electron configurations. Where did the Bohr model come from? Well, it came from a gentleman named Niels Bohr, and he proposed that electrons orbit around the atom's nucleus at very specific levels of potential energy called electron shells. Each shell has a very specific energy level. The closer the shell is to the nucleus, the less energy the electron requires to orbit. So the further out you get away from that nucleus, the more energy you need to put in to get that electron to orbit around. Now again, this only works for about the first 4 rows of the periodic table of elements. We get bigger than that, and we're going to have to get into quantum mechanics. Each electron shell is composed of subshells known as orbitals. And an orbital is defined as a potential space in the electron shell where you can find a pair of electrons 90% of the time. Think of an orbital as being a little box in that orbit, in that electron shell, where if you opened up that box, lo and behold, you would find a pair of electrons. The first electron shell is the shell closest to the nucleus. It has the lowest amount of potential energy, so it doesn't take a lot of energy for the electrons to zip around the atomic nucleus. There is only one orbital in the first shell. It is called the s orbital, and it holds 2 electrons. The s orbital is spherical in shape. Now let's go out one more shell to the second shell. It is comprised of one s orbital holding 2 electrons, and 3 p orbitals, each of which hold 2 electrons. So the 3 p orbitals in combination hold a total of 6 electrons. So if you take the 6 electrons from the p orbitals and add it to the 2 electrons in the s orbital, the second shell holds a total of 8 electrons total. The p orbital, rather than being spherical, is teardropped in shape. The third electron shell is comprised of one s orbital, which holds 2 electrons, 3 p orbitals, each of which hold 2 electrons for 6 total, and 5 d orbitals. Each of the d orbitals holds a pair of electrons. Because there are 5 of them, there are 10 in those 5 d orbitals. 10 plus 6 plus 2 equals 18. So there are 18 electrons that are found in the third shell. Go out one more to the fourth shell. We've got s orbitals, p orbitals, d orbitals, and f orbitals. Each orbital again holds a pair. 32 electrons total. So what do we have? First shell, 2 electrons. Second shell, 8 electrons. Third shell, 18 electrons. Fourth shell, 32 electrons. But here's the thing, folks. Spoiler alert. Only the s and p orbital electrons are capable of participating in bonding reactions. In other words, only the s and p orbitals can form bonds. We don't care about the d, and we don't care about the f. So what I always tell students is I want you to remember this. 2, 8, 8, 8. These are the number of electrons that actually play a role in bonding. 2 electrons in the first electron shell, 8 in the second electron shell, 8 in the third, 8 in the fourth. So just remember that. 2, 8, 8, 8.
Each orbital holds a pair of electrons. So the s orbital holds a pair, the p orbitals hold a pair, each of the d orbitals hold a pair, etc., etc. The s orbitals, we generally have one of those. They will hold 2 electrons. When you get to the p orbitals, there are 3 of them, each of them holding 2 electrons. So p orbitals will hold in total 6 electrons. When you get to the d orbitals, again, each of them hold a pair, and there are 5 d orbitals, so there are 10 total electrons. And then when you get to the f orbitals, there are 7 of those, so the f orbitals have the capacity to hold a maximum of 14 electrons. Now, we don't care about the d and the f orbital electrons because they don't participate in the bonding reactions.
In chemistry, the outermost shell is known as the valence shell. And the number of electrons in the outermost electron shell that are available for bonding are called valence electrons. And these valence electrons, the number of electrons in that valence shell, they are the basis for bonding reactions. The valence electrons are found in s and p orbitals. This is why we don't care about d and f. They are not valence electrons. And the goal of every atom is to completely fill up all of its valence orbitals so that it becomes chemically inert. And once it does that, it is unable to participate in bonding reactions. But the only elements on the periodic table of elements that can fill their valence orbitals without forming bonds are found in column 8. Those are, believe, the noble gases, right? Neon, argon, that kind of stuff. Everything else is going to have an incomplete valence shell, and they're going to have to either steal electrons or share electrons in order to complete their valence orbitals. The periodic table of elements can tell you the electron distributions for each element. You can figure out everything you need to know by the row and column that this element is located in. The rows will tell you basically the number of electron shells that that atom has, and the columns will tell you the number of electrons or the number of valence electrons in the valence electron shell. So for example, if you're in the first row of the periodic table of elements, you have 1 electron shell. If you're in the second row, you've got 2 electron shells. Third row, 3 electron shells. If you're in the first column, you have 1 valence electron in the outermost shell. If you're in the second column, you've got 2 electrons in the outermost valence shell, electron shell, etc., etc. This is why the elements are organized in such a way. I remember I said to my husband, "Oh my God, I didn't realize that about the periodic table of elements." My husband looked at me like I had 4 nostrils and 3 eyes. And I'm going to tell you why. My husband's a chemist. He's like, "Of course that's how you organize the table, the elements on the periodic table of elements. How else do you think they did it?" Well, I'm a biologist, so it didn't occur to me that they're organized based on the number of electron shells and their number of valence electrons. Having learned that, though, now it's pretty easy for me to figure out that carbon has got 2 electron shells and it's got 4 valence electrons in its outermost shell. Why? It's in the second row, 4th column. Here we have some diagrams of some commonly found elements in the human body, and you can see that they've got some information like the number of protons and neutrons in the atomic nucleus, and then they actually diagram the electrons as these little beads. And again, you're thinking this is easy, I've done this before, but I'm going to test this. I'm going to test for this on your exams. So don't dismiss this really easy fundamental stuff. These kinds of materials are things that you can really get some points very easily on exams. So make sure you remember your electron configurations so that you can actually make these points very easily on your exams. The forces holding atoms together are called chemical bonds. And there are different kinds of chemical bonds, but every one of them involve electrons of atoms. Now I can only think of two kinds of bonds, ionic and covalent. So those are the ones that we're going to look at. A molecule is a particle that is formed by the union of more than one atom. You could have this molecule be made of the same kinds of atoms like oxygen, or there can be made of different kinds of atoms like H2O, water. A compound is actually a molecule that is made of different kinds of atoms. So oxygen would be a molecule, and you could also call H2O not only a molecule but a compound. Molecules and compounds are held together by either covalent or ionic bonds. And these bonds are going to form through the interaction between valence electrons. Let's take a look at the ionic bond first. An ion is a charged atom. The number of protons and electrons do not equal one another. So an ionic bond is an attraction between two oppositely charged atoms, or two oppositely charged ions. For example, positively charged sodium will form an ionic bond with negatively charged chlorine to end up with sodium chloride. Positively charged calcium and negatively charged chloride form calcium chloride. Ions form as one atom either gains or loses electrons. If you lose an electron, you become a positively charged ion known as a cation. And if you gain an electron, you become a negatively charged ion known as an anion. For every electron that you gain or lose, your charge changes by 1. Ionic bonds form as one atom transfers electrons to another atom. So, simply put, ionic bonds form between cations and anions. So here we have a picture of sodium, which is going to have one electron in its outermost electron shell. It has one valence electron. Now remember the numbers 2, 8, 8, 8. So let's take a look at sodium. It's got 1, 2, 3 electron shells. That means in order to become chemically inert, it is going to have 8 electrons in that third shell. Well, it's got 1 already, so it's going to have to pick up 7. Ask yourself this question though. If you were sodium, what would be easier? To steal 7 more electrons, or just to get rid of that 1 electron and end up with 2 electron shells? The second electron shell having the 8 complete valence electrons in your orbitals. I'd personally want to just get rid of my 1 electron and be happy with 2 complete electron shells. Take a look at chlorine. Chlorine basically has 7 electrons in its outermost electron shell. What's going to be easier, picking up 1 or getting rid of 7 electrons? Well, it wants to pick up 1, and it just happens to get that electron from sodium. Sodium is going to donate the 1 electron it doesn't want to become a positively charged cation, and chlorine is going to pick up that electron to become a negatively charged ion called chloride. An ionic bond will form between the sodium and the chloride ions. Most of your group 1A and group 2A metals will form ionic bonds with the group 7 halogens. So columns 1 and 2 and column 7 will form ionic bonds. And they tend to form really well-ordered crystalline structures. For example, here you can see the packing of sodium and chloride ions in a very well-organized crystalline structure. Ions may also be composed of more than one atom. These are known as polyatomic ions. These are treated the same as monoatomic ions. So they're treated the same way as sodium ions and chloride ions. In physiology, the most common polyatomic ions are the phosphate ion with a charge of -3, the sulfate ion with a charge of -2, nitrite with a charge of -1, and hydroxide with a charge also of -1. This table also gives the common polyatomic ions that chemists would look at, but as physiologists, we're interested in things like phosphate, sulfate, the nitrite, hydroxide. We'd also be interested in, believe it or not, acetate is another important one. Cyanide might be important if you're trying to poison somebody. And another one which is very important to a physiologist is bicarbonate. If it isn't favorable or possible for an atom to either gain or lose electrons, it's going to have to share them with another atom. And the sharing of electrons so that each atom can complete its valence electron shell, that's going to form a covalent bond. A covalent bond is a bond in which atoms share valence electrons. And the covalent bonds are usually going to form when an atom has to gain or lose 3 or more electrons. Take carbon as an example. It's got 4 electrons in its outermost valence electron shell. It's got a valence of 4. So we would either have to lose those 4 electrons or gain 4 electrons in order to complete the outermost shell. Nitrogen would have to gain 3. That's really hard for an atom to do, so that's why they decide to partner up with another atom and share their electrons. So nitrogen says, hey, why don't I partner up with another nitrogen? We can share 6 electrons, and lo and behold, we have 8 in our outermost valence electron shell. Now we're happy. Covalent bonds form between identical atoms, like to form nitrogen gas or oxygen gas. They can also form between different atoms. This slide outlines covalent bonds for you, the physiologist. It lists some of the commonly seen elements in the human body, their valences, and the number of electrons needed. Now let me clarify something about valence. Valence electrons are those electrons in the outermost valence shell that participate in bonding. So there are 2 ways you can answer a question of what's the valence. If you looked at oxygen, it's in column 6. So technically, the valence is 6. However, 2 out of those 6 electrons are going to participate in covalent bonds. So you could also answer the question that oxygen has a valence of 2. So on an exam, it is possible for me to ask you the valence of a particular element, and you can give me one of 2 possibly correct answers. Nitrogen in chemistry, you probably learned it has a valence of 5. However, only 3 out of those 5 valence electrons will form a bond. So you could also answer that nitrogen has a valence of 3. Don't worry about it, okay? It's up to me as the professor to know whether or not an exam question has more than one correct answer. You just have to know one of the correct answers. I have to know all of the correct answers. So we can now modify the definition of a molecule even further. A molecule consists of 2 or more atoms held together by covalent bonds. A single covalent bond or a single bond is the sharing of 1 pair of valence electrons. It's usually denoted with the structural formula with H and a dash H, and that little dash in the center is basically the shared electrons. The double covalent bond or double bond is the sharing of 2 pairs of valence electrons. You can see there's 2 dashes. Again, each one of those lines represents the sharing of a pair of valence electrons. And of course, there's a triple covalent bond, which is the sharing of 3 pairs of valence electrons. The sharing of electrons can either be equal or unequal. The equal sharing of electrons between 2 atoms produces a non-polar covalent bond. Carbon is probably the most commonly found atom that's in a non-polar covalent bond. So carbon-containing compounds like methane. Gases also are held together by non-polar covalent bonds. The unequal sharing of electrons between 2 atoms produces the polar covalent bond, and a lot of oxygen-containing compounds will have polar covalent bonds. The thing about the polar covalent bond is the unequal sharing creates a slight positive and negative charge within the molecule, as one atom pulls harder on an electron pair than the other one. Let's take a look at the nonpolar and polar covalent bond a little bit more closely. In a nonpolar covalent bond, the atoms are going to share their electrons equally. This is because the 2 atoms are equally electronegative. they pull equally on those electrons. Carbon is an excellent example of an atom that will form nonpolar covalent bonds. Particularly, it will form nonpolar covalent bonds with other carbon atoms or with hydrogen atoms. And when you see this picture here of methane, CH4, you can see that the shared electron pairs are equidistant between the hydrogen atom's nucleus and the carbon atom's nucleus. This is because carbon and hydrogen are pulling on those shared electron pairs equally. Think of it as a tug of war competition in which the two teams are pulling on the ropes equally so that nobody moves. In a polar covalent bond, one atom is said to be more electronegative. And as a result, the atoms within this molecule that have the electronegative atom are not shared equally. This is because the electrons are going to spend more time around the electronegative atom than the non-electronegative. And that leads to an unequal sharing of electrons. I think of it as a tug of war in which one team is slightly stronger than the other one and can pull on the rope harder, so that that little flag between the two teams ends up moving closer to the stronger tug of war team. What you end up with is a distortion of the orbit of the non-electronegative atom. Take a look at this picture of H2O. The oxygen is the more electronegative atom. It's going to pull on the electron pair harder than hydrogen can pull back. And you can see that the orbit of this hydrogen is slightly distorted. It almost loses its electron. This electron pair is further away from the hydrogen atom's nucleus and closer to the oxygen atom's nucleus. This results in a slight positive charge to the hydrogen and a slight negative charge to the oxygen. And we denote this slight negative charge with the Greek letter delta. Again, this can happen with oxygen-containing compounds because oxygen is very electronegative, so it creates polar bonds, but nitrogen is also very electronegative.
Our next mini lecture in this series is Lecture 1C, and Lecture 1C is going to talk about chemical reactions and things like enzyme catalysts, which can speed up those chemical reactions.